Look up at the night sky on a clear, dark evening, far from the glow of city lights. You see a river of stars, the majestic arch of our own Milky Way galaxy. A breathtaking tapestry of light stretching from horizon to horizon. It feels complete, a vast and glittering whole, but look closer. Within that brilliant expanse, there are patches of absolute blackness. Not just the simple dark of an empty sky, but profound, velvety voids that seem to swallow the light itself. For centuries, astronomers saw these as mere gaps, empty lanes in the cosmic traffic of stars. What if I told you that these apparent voids of nothingness are actually some of the most mysterious and crucial structures in our entire galaxy? These are not absences, they are presences, they are dark nebulae. Imagine a cloud, but not one made of water vapor. This is a cloud of cosmic dust and gas so incredibly dense, so thick with microscopic grains of carbon and silicate, that it completely blocks the light from the stars behind it. It creates a silhouette against the brilliance of the galaxy, a shadow so vast it can be seen from countless light years away. These are the places where light goes to die, and in that darkness, something incredible is happening. Today, we are going on a journey into that very darkness. We are going to explore 25 specific dark nebulae that do more than just hide stars. They challenge the very foundations of our understanding. They are cosmic puzzles, each one raising profound and unsettling questions that touch on the deepest mysteries of the universe. How do stars truly ignite from such oppressive gloom? What bizarre and complex chemistry is brewing inside these lightless nurseries? Could the very fabric of space and time behave differently within their in-sky depths? This is not just a tour of cosmic landmarks. This is an investigation into the unknown, a voyage to the frontiers of our knowledge where the answers we find might be more strange and wonderful than any fiction. So, let's pull back that curtain of darkness together and discover what secrets these enigmatic clouds have been keeping from us. Our journey begins not with a brilliant star or a colorful gas cloud, but with a profound patch of emptiness known to sky watchers for millennia. Gazing toward the iconic Southern Cross, you can see it with your own eyes, the Coalsack Nebula. It appears as a stark, black void, a tear in the fabric of the Milky Way, as if a giant ink blot has been spilled across the stars. This is no mere gap. It is a monumental, three-dimensional structure, a cloud of cosmic soot so dense and vast that it blots out the light from the hundreds of thousands of stars that lie behind it. At a distance of about 600 light-years, it stands as one of the very closest dark nebulae to our own solar system, a next-door neighbor in galactic terms. But its familiarity only deepens the mystery. What is this colossal cloud actually made of? Within its frigid, lightless heart, temperatures hover just a dozen degrees above absolute zero. In that deep freeze, exotic ices water, of course, but also methane, ammonia, and even more complex organic molecules coat every microscopic speck of dust like frost on a window pane. This isn't just simple dirt. It's a rich chemical soup, the very precursor to the building blocks of life, frozen in time and suspended in the darkness. By mapping the Coalsack's intricate internal structure with radio and infrared telescopes, which can pierce its obscuring veil, astronomers use it as a living laboratory to understand the initial conditions from which stars are born. We can see the subtle clumps and filaments that may one day contract into stellar nurseries. Yet, for all our observation, a fundamental question remains stubbornly unanswered. We see the ingredients and the potential, but we don't know the exact recipe. What is the final, critical trigger that causes a stable, massive cloud like the Coalsack to suddenly and violently collapse under its own weight, igniting the furious fire of new stars? Is it the shockwave from a distant supernova, a chance encounter with a spiral arms gravitational density wave? The cloud holds its secrets close, a silent, brooding giant on our cosmic doorstep, reminding us that the very first step in the birth of a sun is still one of the universe's most closely guarded mysteries. From the sprawling expanse of the Coalsack, we now turn our attention to a much smaller, yet infinitely more intricate, shadow in the cosmos. Slithering through the star-rich fields of the constellation Ophiuchus, you'll find a dark nebula so perfectly formed it seems almost deliberate. This is the Snake Nebula, known to astronomers as Barnard 72. Unlike the vast, blotchy darkness of the Coalsack, the Snake is a slender, sinuous ribbon of cosmic dust, winding its way through the background starlight with an almost artistic elegance. It's a captivating sight, a celestial serpent frozen in mid-motion, but its beautiful form points to a deeper cosmic reality. The Snake Nebula is a textbook example of what's known as a Bach globule. These are small, isolated, and incredibly dense clouds of gas and dust, often described as the final, compacted stage of a dark nebula's life, just before it gives birth to stars. They are the cosmic equivalent of a tightly clenched fist, holding within them the potential for new solar systems. This is where the mystery of the snake truly begins. Its iconic, coiled shape is not just a random accident. What cosmic forces could sculpt such a distinct, serpentine structure from a formless cloud? The leading theories are a cosmic tug of war. Intricate magnetic fields threading through the galaxy could be channeling and confining the dust, twisting it into these long, filamentary shapes. Alternatively, powerful turbulence within the cloud itself, the chaotic churning of internal motions, might be responsible for stretching and folding the material. Or perhaps, the relentless pressure and stellar winds from brilliant, massive stars in its vicinity are slowly carving and compressing the cloud, like a sculptor working on a block of marble. We observe the beautiful result, but the exact tools used by the universe remain hidden. An even more puzzling question surrounds the snake's apparent stillness. As a prime Bach globule, it's brimming with the ingredients for star formation, and yet, it shows no signs of the vigorous stellar birth we might expect. It seems to be in a state of cosmic suspended animation. What invisible support is holding it up, preventing its inevitable gravitational collapse? The internal pressure of the gas itself, or the support provided by those same magnetic fields that may have shaped it, could be providing just enough resistance to keep gravity at bay. It's a delicate and protracted standoff, a pause that could last for millions of years before the delicate balance is finally upset, and the serpent's dark belly finally begins to glow with the first, faint light of newborn suns. This tiny, dark thread in space forces us to confront the subtle and complex physics that govern the very beginning of a star's life. Leaving the delicate serpent of Ophiuchus behind, we now journey to one of the most famous and hauntingly beautiful silhouettes in the entire night sky. In the sword of the mighty hunter Orion, hanging just below his iconic belt, lies a cosmic sculpture so perfect it seems almost impossible. This is the Horsehead Nebula, a dark pillar of dust known as Barnard 33, standing in stark, breathtaking relief against the faint, pinkish glow of the emission nebula IC434. That glowing backdrop is hydrogen gas, energized by the fierce light of brilliant young stars, and it makes the Horsehead's profile unmistakable, a knight in a cosmic chess game, or a seahorse rearing up from a sea of light. Its fame is undeniable, a true celebrity of the cosmos, but this celebrity status comes with a sobering reality. The very thing that makes the Horsehead visible is also leading to its destruction. Just to the south of this dark titan lies Sigma Orionis, a massive, intensely hot star system. This stellar powerhouse doesn't just emit visible light, it floods its surroundings with a torrent of blistering ultraviolet radiation. This UV radiation is so energetic that it is quite literally boiling the Horsehead Nebula away, molecule by molecule, in a process astronomers call photodissociation. Imagine a block of ice placed under a scorching desert sun. The surface doesn't just melt, it directly turns from solid to vapor. A similar, though far more violent, process is happening to the Horsehead. The ultraviolet photons from Sigma Orionis are slamming into the nebula's surface, stripping electrons from atoms and breaking apart the delicate molecular structures that have clung to the dust grains for eons. This creates a very thin, highly active layer on the nebula's illuminated edge, known as a photodissociation region. It's a cosmic frontier, a battlefield where the ordered structure of the cold, dark nebula meets the chaotic energy of starlight. And this is where the central, poignant mystery of the Horsehead emerges. We can watch this evaporation happening in real time, but we cannot yet precisely answer the question: how much longer will this iconic shape grace our skies? Accurately modeling its evaporation rate is an immensely complex challenge. It's not a simple matter of calculating how quickly a single block of material is vaporizing. The Horsehead is a complex, three-dimensional structure with varying densities, intricate magnetic fields, and a deeply turbulent internal chemistry. Some parts of the cloud are denser and more resistant to erosion, while more tenuous sections are being scoured away far more rapidly. Furthermore, the photodissociation region itself is a cauldron of exotic physics. As the radiation breaks molecules apart, it triggers a cascade of new chemical reactions in the gas, some of which can actually form new, more complex molecules right at this violent interface. The very process of destruction might also be a process of creation, adding another layer of complexity to predicting the nebula's lifespan. Current estimates suggest we may have this celestial landmark for another 5 million years or so, but that is a rough guess at best. The true timeline depends on a delicate balance of forces we are only beginning to understand, reminding us that even the most seemingly permanent and iconic features of our universe are merely transient visitors in the vast flow of cosmic time. But while the Horsehead is a masterpiece of erosion, our next destination presents a structure of an entirely different magnitude. If you trace a line from the bright star Antares in Scorpius toward the center of our galaxy, you might notice a long, dark river splitting the star clouds of Sagittarius. This is the Pipe Nebula, a celestial landmark so vast and distinct that it's visible to the naked eye under a truly dark sky. It appears as a long, dark stem leading to a bowl, a cosmic pipe waiting to be filled with starlight. The sheer scale of this object is what first captures the imagination. This is not a single, isolated cloud like the Snake Nebula. The pipe is a sprawling complex, a collection of several distinct dark nebulae catalogued by astronomer Barnard, primarily Barnard 59, which forms the bowl, and Barnard 65, 66, and 67, which create the long, elegant stem, all part of the larger Barnard 78. Together, they form one of the most prominent dark cloud complexes in our entire sky, a monolithic structure composed of some of the coldest, most pristine material in our galactic neighborhood. The questions this colossal cloud raises are as immense as the nebula itself. How does such an extensive and coherent structure, spanning dozens of light years, even form and hold itself together? It's not a single, collapsing blob. It's a network, a web of dark filaments connected by gravity's invisible threads. Astronomers believe these colossal complexes are the fundamental building blocks of the galaxy's molecular cloud structure, the great reservoirs from which thousands of stars will eventually be born. Their formation is likely tied to the large-scale dynamics of the Milky Way itself, the collective gravitational pull of the galaxy's spiral arms, the shockwaves from ancient supernova, and the intricate interplay of turbulence and magnetic fields on a truly galactic scale. The Pipe Nebula, in its relative quiet, offers a frozen snapshot of this process, a moment of calm before a storm of stellar birth. Yet, its apparent tranquility is deceptive. The most intense research today focuses on peering into its darkest, most opaque lanes to map the distribution of its mass with incredible precision. using telescopes that see in the far infrared and submillimeter wavelengths, which can sense the faint heat emitted by the dust itself. Scientists are creating a three-dimensional inventory of the cloud's contents. They are finding that the material is not smoothly distributed. Instead, it's clumped and fragmented into dense cores, many of which are massive enough to one day form not just sun-like stars, but brilliant, short-lived, colossal O-type stars, the true powerhouses of the galaxy. This leads to the most compelling mystery hidden within the pipe's darkness. We see the potential, the raw material gathered and waiting, but what we don't yet know is the timeline. When will the final, critical gravitational threshold be crossed in its densest cores? What will be the trigger that finally shatters this colossal cloud's equilibrium and ignites a fireworks display of stellar formation that could reshape its entire region of space? The Pipe Nebula stands as a silent, looming promise of a spectacular future cosmic event, a testament to the fact that some of the universe's most dramatic transformations begin in the deepest, most profound silence. After exploring the sprawling, complex filaments of the Pipe Nebula, we now encounter a dark nebula that is the very definition of simplicity and perfection. In the constellation of Ophiuchus, a region we've visited before, lies an object so starkly different it almost seems artificial. This is Barnard 68, an ink-black sphere suspended against a rich backdrop of stars. If the Snake Nebula is a winding river of dust, then Barnard 68 is a perfectly formed droplet. It's so circular, so symmetrically dark, that it looks less like a celestial object and more like a hole punched through the universe, a portal to nothingness that has earned it the nickname the Ink Spot. This seemingly simple void is, in fact, one of the most instructive and puzzling dark nebulae we have ever found. Its perfect spherical shape is the first great mystery. In a universe dominated by chaos, turbulence, and twisting magnetic fields, how does a cloud of gas and dust achieve such geometric perfection? For a shape this precise to form and persist, the cloud must be in a state of remarkable equilibrium. The inward pull of its own gravity must be perfectly balanced by an outward pressure, likely from the heat of the gas trapped within its dense core. It's a cosmic balancing act of incredible delicacy. This suggests that Barnard 68 is an exceptionally stable and isolated Bach globule, one that has been left undisturbed by the gravitational tugs of nearby stars or the shockwaves from distant supernova for a very long time. It has had the quiet solitude necessary to settle into this flawless form, a calm bubble in the turbulent galactic ocean. But this beautiful symmetry points directly to an even more profound question. Is this serene stability merely the calm before an epic storm? Is Barnard 68 poised on the very brink of gravitational collapse, a frozen moment just before it gives birth to a star? The cloud's pristine darkness provides the perfect conditions for astronomers to investigate this very possibility. Because it blocks virtually all visible light from the stars behind it, it acts as a natural cosmic laboratory. By observing how the light from these background stars is dimmed and reddened as it passes through the nebula's outer layers, scientists can create a detailed map of the cloud's density from its edge to its very center. What they find is a cloud that is incredibly dense and cold, with conditions that seem ripe for collapse. Yet, the crucial, unresolved mystery lies at its heart. What is happening in the absolute center of this perfect sphere? Is there a dense core there, a secret protostar already slowly turning, gathering mass, and preparing to ignite its nuclear furnace and blaze forth, shattering the globule's dark harmony? Or, perhaps more intriguingly, is the center just as cold and pristine as the outer layers, a perfectly preserved pocket of the original molecular cloud from which our galaxy was built, a sample of primordial material untouched by stellar processes? The answer defines the nebula's entire future. If a protostar is forming, Barnard 68 is a stellar womb in its final moments of pregnancy. If not, it remains a timeless relic, a perfectly preserved snapshot of the raw ingredients of the cosmos, holding within its dark, spherical heart the potential for a future that has not yet begun. Now we head deep into the southern skies, far from the familiar constellations of the north, to a small but striking constellation called Musca, the Fly. Here, against a dense backdrop of Milky Way stars, you will find one of the most extraordinary dark nebulae known to observers, the dark Doodad. The name might sound whimsical, but its appearance is anything but. This nebula presents itself as a long, impossibly straight, and silent river of absolute black, slicing through the starry expanse with the sharp, clean lines of a cosmic scar. It doesn't meander or coil. It simply stretches across the sky for over 3 degrees, a vast, linear silhouette that seems almost too perfect to be a natural formation. This remarkable linearity is the source of its first great mystery. In a universe where turbulence and chaos are the norm, what incredible force could possibly sculpt a cloud of gas and dust, light years in length, into such a pristine, filamentary shape? The prevailing theory points to the invisible architecture of the galaxy itself, the vast, interwoven magnetic fields that permeate interstellar space. It's possible that the material comprising the dark Doodad is channeled, constrained, and pulled into alignment along the lines of a powerful magnetic field, much like iron filings arranging themselves along the field lines of a magnet. This would create the remarkably straight, thread-like structure we observe. However, an alternative, equally compelling idea suggests that the Doodad might be the result of a colossal, ancient shockwave. The explosive force of a nearby supernova, or the sheer gravitational pressure of a passing spiral arm, could have compressed a wide cloud of material into a long, thin sheet, a ripple frozen in time. We see the magnificent result, but the precise sculptor's hand remains hidden, a testament to the powerful yet unseen forces that shape the cosmos on the grandest scales. But the dark Doodad is not an isolated entity. It is the most visible and dramatic part of the larger Musca molecular cloud complex, a vast reservoir of cold gas and dust from which future stars will be born. And this relationship introduces an even more intriguing puzzle. When astronomers peer into the Doodad with telescopes that can see past its dark veil, they find a paradoxical situation unfolding. Along certain segments of this long, dark river, the process of star formation has begun. Dense cores within the filament have crossed the gravitational threshold, collapsing to ignite new protostars. Yet, in other sections of the nebula, seemingly identical in their darkness and density, everything remains perfectly still and quiescent. This stark contrast forces a fundamental question about the very triggers of stellar birth. Why here and not there? If the entire filament formed under the same conditions, why is star formation so patchy and localized? The answer likely lies in subtleties we are still learning to detect. Perhaps the quiescent sections are stabilized by stronger internal magnetic fields, or greater internal turbulence that provides extra support against collapse. Maybe the triggering event, like the shockwave from a distant star's death, has only reached certain parts of the cloud so far, like a wave washing over only part of a shoreline. Or it could be that the chemical makeup varies slightly along the filament's length, with some regions having just enough more complex molecules on the dust grains to help cool the gas faster, allowing gravity to win the battle more easily. The dark Doodad, in its elegant simplicity, presents a brilliant natural experiment, a controlled laboratory in the sky where we can study the fine-grained differences between a cloud that is ready to create stars and one that is content to simply wait. Now, let's turn our gaze upward to one of the most prominent, yet often overlooked, features of the entire night sky, the Great Rift. If you've ever looked at the summer Milky Way arching overhead and noticed that it appears to be split into 2 roughly parallel streams of stars by a long, winding band of darkness, you have seen the Cygnus Rift. This is not a single nebula, but an immense, sprawling complex of overlapping dark nebulae, a cosmic labyrinth that stretches from the constellation Cygnus all the way down to Sagittarius, obscuring the very heart of our galaxy. The scale of this structure is almost beyond comprehension. We are not looking at a single cloud, but at a towering wall of dust, a series of colossal curtains hanging in space, composed of countless individual clouds catalogued by Barnard and other astronomers. Together, they form a dark river so vast it fundamentally shapes our entire perspective of the Milky Way. And this leads directly to the first, and perhaps most fundamental, puzzle: the Cygnus Rift presence. When we look at this magnificent dark band, we are seeing a two-dimensional projection on the celestial sphere. We have no innate depth perception for such distant objects. So, the central challenge for astronomers has been to untangle this grand illusion, to determine which of these dark clouds are relatively close to us, and which are thousands of light years farther away, layered one in front of the other like pages in a cosmic book. Solving this three-dimensional puzzle is crucial, because the distance to each cloud determines its true physical size and mass, which in turn tells us about its role in the galactic ecosystem. How do we even begin to map this? The primary tool is a technique called star counting. By carefully measuring how much the light from vast numbers of background stars is dimmed and reddened by the intervening dust, and by analyzing the precise spectral types and known luminosities of those stars, scientists can construct a statistical model of the dust's distribution along our line of sight. It's a painstaking process, akin to figuring out the shape and position of a cloud by standing on the ground and noting how many of the sun's rays it blocks. These efforts have revealed that the Cygnus Rift is not a single, monolithic wall, but a series of dust clouds at varying distances, with some of the nearest components, like the cloud in front of the star Deneb in Cygnus, lying only a few hundred light years away. This intricate mapping reveals a stunning reality. We live inside a rugged, dusty landscape, and our view toward the galaxy's center is like looking through a series of frosted windows, each with a different level of grime. This brings us to the rift's most profound influence. This colossal reservoir of dust doesn't just hide a few random stars. It completely obscures our optical view of the galactic core. The brilliant, bustling center of the Milky Way, a region teeming with stars and activity, is entirely veiled from our sight in visible light by the accumulated dust of the Cygnus Rift and other complexes like it. We are, in a very real sense, living in the galactic suburbs, with our view of the downtown core blocked by a range of dark, cosmic mountains. This is why the true nature of the galactic center remained one of astronomy's greatest mysteries for so long. It was only when we developed telescopes that could see in other wavelengths, radio, infrared, and X-rays, that we could pierce this dusty veil and finally witness the incredible activity at the heart of our galaxy. The supermassive black hole, the dense clusters of stars, and the violent processes that are completely invisible to our eyes. The Cygnus Rift, therefore, is more than just a collection of dark clouds. It is a defining feature of our cosmic perspective, a reminder that what we see in the night sky is not the whole story, but merely the part of the universe that the dust allows us to see. Shifting our perspective from the grand, sweeping structures of the Cygnus Rift, we can zoom in on a single, peculiar dark nebula that demonstrates just how dynamic these shadows can be. Located in the constellation of Ophiuchus, LDN 1774 appears as a cosmic tadpole, a dark, teardrop-shaped core with a brilliantly illuminated rim. This isn't a static, brooding cloud like Barnard 68. It looks as if it's actively moving, plowing through space, with its bright edge glowing from the intense radiation it's encountering. The form is so distinct it's categorized as a bright-rimmed cloud, and its very shape is a story written in light and shadow. That glowing rim is a telltale sign of a photodissociation region, a violent interface where the cold, ordered molecules of the dark nebula are meeting a torrent of energy. The ultraviolet radiation is so fierce that it ionizes the gas at the cloud's surface, stripping electrons from atoms and causing it to fluoresce, much like the glowing gas in a neon sign. This radiation is also exerting a physical force, a constant, unrelenting pressure that is compressing the cloud, sculpting it into that streamlined, cometary shape. This immediately presents us with a compelling cosmic detective story. We can see the effect the cloud is being shaped and eroded, but the culprit is not immediately obvious. What is the brilliant, massive star providing this intense, sculpting light? Is it a single, nearby O-type star that we simply haven't pinpointed yet, perhaps hidden behind another veil of dust? Or is the radiation source more diffuse, the combined output of an entire stellar association, a group of hot, young stars whose collective ultraviolet glow is washing over this region of space? Identifying the precise source is more than an academic exercise. It's crucial for understanding the future of this cloud and everything inside it. That's because LDN 1774 is a premier natural laboratory for studying one of the most debated concepts in star formation: triggered birth. The theory is elegant and compelling. The radiation-driven shockwave compressing the cloud doesn't just shape it. It can also initiate a chain reaction within. As the external pressure increases, it can squeeze dense cores deep inside the globule past their critical point, overwhelming their internal support and forcing them to collapse into new stars. It's a classic cosmic domino effect, where the death throes of one generation of stars, in the form of intense radiation, can trigger the birth of the next. We see evidence that supports this. In many bright-rimmed clouds, including LDN 1774, astronomers have found young stellar objects and protostars nestled right up against the illuminated rim, suggesting their formation was catalyzed by the advancing shock front. Yet, the debate among scientists is far from settled. The central, unresolved question is one of timing and causality. Are we truly witnessing a trigger, where the external pressure initiated a collapse that would not have otherwise happened for millions of years? Or is this simply a case of convergence, where the cloud was already on the verge of collapsing on its own, and the external radiation pressure just happened to arrive and compress the cloud a little faster, making it look like the prime cause? The newborn stars we see near the rim might have been destined to form anyway, and the external shock merely shaped the where and when of their birth, not the if. Disentangling this sequence of events is incredibly difficult. It requires precise measurements of the ages of the young stars inside the cloud and the surrounding stars providing the radiation, as well as a detailed understanding of the cloud's internal dynamics before the shockwave hit data that is often frustratingly incomplete. So, while LDN 1774 stands as a beautiful and seemingly clear-cut example of a cloud being shaped and potentially triggered by its environment, it simultaneously highlights a fundamental uncertainty in our understanding of stellar genesis. The universe, it seems, enjoys blurring the lines between cause and coincidence, even in the act of creation itself. Continuing our exploration of these cosmic sculptures, we arrive at perhaps the most iconic dark pillar of them all, the magnificent Cone Nebula. Nestled within the larger star-forming complex known as NGC 2264, in the constellation Monoceros, the cone presents a sight of breathtaking grandeur. It rises from a murky sea of glowing gas like a colossal, dark tornado, a stark, pointed finger of dust and gas that seems to defy the brilliant chaos surrounding it. Its most famous feature, aside from its sheer, monolithic presence, is its precise orientation. The tip of the cone points directly away from the brilliant, young stars of the Christmas tree cluster, a collection of hot, massive suns that illuminate the entire region. This is no cosmic coincidence. It is a direct clue to the forces that carved this incredible structure. The Cone Nebula is a masterpiece of destruction. The powerful stellar winds and blistering ultraviolet radiation blasting from the massive stars of the cluster are acting like a cosmic sandblaster, relentlessly scouring away the less dense material of the original molecular cloud. The pillar itself is what remains, a dense core of gas and dust that has so far withstood the onslaught. The material at the very tip of the cone is the most shielded, protected by the long column of dust behind it, while the flared base bears the full brunt of the erosive forces. This ongoing process creates the nebula's stunning, sharp profile, a natural monument to the violent interplay between the life-giving material of dark nebulae and the life-ending power of the stars they create. Yet, for all its iconic beauty, the Cone Nebula guards a central secret at its very peak. What lies hidden in that dark, sheltered tip? Is it a true stellar nursery, a dense core where a protostar is actively gathering mass, hidden from our view by the very dust that protects it? Or is it a starless core, a final, dense lump of primordial material that has so far resisted the ultimate gravitational collapse? This is not merely an academic question. The answer defines the very purpose and future of the entire pillar. Observations with infrared and submillimeter telescopes, which can peer through the obscuring dust, have provided tantalizing but complex clues. They reveal several bright infrared sources in the vicinity, suggesting young stellar objects are indeed embedded within the pillar's structure. However, pinpointing a single, definitive protostar right at the very tip has proven challenging. The data suggests there is certainly a concentration of mass there, a dense knot that could be on the verge of collapse, but confirming active accretion. The telltale sign of a true protostar in the making requires even more sensitive observations. The environment is so complex, with emission from the surrounding heated dust and gas, that isolating the signal from a single, nascent object is like trying to hear a whisper in a roaring hurricane. This leads us to the broader, more profound mystery of all such pillars. From the cone to the famous structures in the Eagle Nebula, how do they manage to survive at all? The radiation and winds they face are unimaginably powerful, capable of dispersing a cloud of this scale in a relatively short period of cosmic time. The prevailing theory is that their longevity is intimately tied to their role as stellar cradles. The pillars may be anchored by gravity specifically, the gravity of the dense cores and any protostars forming within them. This inward pull provides a crucial counterbalance to the external forces of erosion, allowing the pillar to hold its shape for longer than a simple cloud of dust ever could. In this view, the star formation isn't just happening in spite of the destruction. It is the very reason the pillar still exists to be seen. It's a race against time, where the gravitational collapse of new stars within must happen quickly enough to outpace the evaporation of the pillar from without. If no protostar is present at the tip of the cone, its fate is far more certain and swift. Without that gravitational anchor, the entire structure is just a temporary shape in the wind, a fleeting sculpture that will be completely eroded and swept away by the relentless stellar fury. Its raw materials recycled into the interstellar medium to one day form part of another cloud, another star, another world. So, the dark tip of the Cone Nebula is more than just a point of shadow. It is a frontier. It represents the delicate threshold between a structure that is a true incubator of new solar systems and one that is merely a ghost, a magnificent but ephemeral remnant of a cloud that once was. From the sculpted majesty of the Cone Nebula, we now travel to a region that is less about dramatic destruction and more about prolific, almost business-like creation. In the southern constellation of Lupus, the Wolf, lies Lupus III, a dark nebula that presents a stunning celestial diorama of birth and infancy. What sets this cloud apart is its breathtaking duality. It is a place of deep, brooding dust lanes, classic rivers of blackness that coil through space. But these are punctuated by brilliant, diamond-like points of light, dozens of young, variable stars known as T-Tauri stars. These are not the massive, short-lived giants that illuminate and erode nebulae like the cone. These are stellar infants, suns similar to our own in its earliest, most tempestuous phase of life. They are the newborns of the cosmos, still accreting material from their surrounding disks and flashing with the intense magnetic activity of youth. The nebula itself acts as both their cradle and their backdrop, with the dark dust providing a stark, velvety canvas that makes the light of these infant stars pop with incredible clarity. This vibrant juxtaposition immediately raises a compelling question for astronomers. While many dark nebulae seem to form stars in a slow, sporadic trickle, Lupus 3 appears to be a veritable stellar production line, a highly efficient nursery. What is the special ingredient in this cloud's recipe that makes it so prolific? The answer appears to lie not in what we can easily see, but in the invisible forces that orchestrate the collapse of gas. The prevailing theory points directly to the cloud's magnetic field. In most molecular clouds, magnetic fields provide a crucial form of support, acting like a scaffold that holds the cloud up against its own gravity, slowing down the process of collapse. In Lupus 3, however, the magnetic field seems to have a unique and more permissive configuration. Observations suggest that the field lines running through the cloud are remarkably well-ordered and aligned over large scales. This organization is thought to be a key factor in its efficiency. When magnetic field lines are chaotic and tangled, they create a kind of magnetic turbulence that can prevent material from flowing smoothly inward. But when they are orderly, like the straight lines of a comb, they can actually channel and guide the flow of gas along their length, facilitating a more controlled and efficient collapse into dense cores. It's the difference between trying to pour water through a tangled thicket versus a smooth, sloped gutter. In Lupus 3, the gutter is in place, allowing the raw material for stars to stream together with less resistance. This brings us to the central and deeply challenging puzzle of Lupus 3. While we have strong indirect evidence for this influential magnetic field, directly measuring its precise three-dimensional structure and exact strength within the opaque depths of the cloud is one of the most difficult tasks in modern astrophysics. The primary method relies on a phenomenon called starlight polarization. As light from distant background stars passes through the long, needle-like dust grains aligned by the magnetic field within Lupus 3, it becomes subtly polarized. By carefully measuring the orientation of this polarization across the entire cloud, astronomers can effectively trace the projected two-dimensional direction of the magnetic field on the plane of the sky. It's like seeing the shadow of the field, a hint of its overall orientation. But this two-dimensional map is only part of the story. We are still largely blind to the field's component along our line of sight, its true three-dimensional shape, and most importantly, its absolute strength. How much magnetic energy is actually woven through this cloud? And how does that force precisely balance against the turbulent motions of the gas and the relentless pull of gravity? Without knowing the strength, our understanding of the cloud's dynamics remains incomplete. We cannot be certain if the field is the dominant force guiding the star formation, or merely a contributing player in a more complex ensemble of forces. New techniques, such as measuring the Zeeman effect in radio frequencies, a tiny splitting of spectral lines caused by the magnetic field, offer a way to probe this strength. But these observations are incredibly challenging and data is sparse. So, Lupus 3 stands as a paradox, a dark nebula whose greatest secret is held not in its dust or its stars, but in the invisible, magnetic architecture that binds them together. It is a cosmic factory whose blueprints we can only partially decipher, reminding us that even in our most detailed observations of the cosmos, some of the most fundamental forces remain just out of reach. Yet, even the formidable pillars we've seen are dwarfed by the sheer violence faced by our next subjects, a collection of dark specks that seem to be defying the laws of astrophysics. In the southern constellation, Centaurus, within the sprawling, brilliant glow of the emission nebula IC 2944, lies a scene of both beauty and brutality. Here, against a backdrop of pink, hydrogen gas energized by some of the galaxy's most massive and luminous stars, you can find Thackeray's globules. These are not the grand, sculpted pillars of the Cone Nebula. They are small, isolated, and incredibly dense knots of darkness, appearing like a school of cosmic tadpoles swimming serenely through a luminous sea. Their forms are compact and teardrop-shaped, with faint, glowing rims where they are being bombarded by an unimaginable torrent of ultraviolet radiation. The stars responsible for this onslaught are O-type giants, stellar behemoths that live fast and die young, flooding their surroundings with enough energy to tear apart any ordinary cloud of gas and dust in a cosmic heartbeat. This is where the profound mystery of Thackeray's globules begins. Given their small size and isolated nature, basic physics suggests they should have been completely evaporated and scattered into the interstellar void eons ago. The radiation pressure alone should have been sufficient to pop these delicate bubbles of dust. And yet, there they are, persisting against all odds. Their mere existence presents a direct challenge to our understanding of the balance between destructive and cohesive forces in space. How can such seemingly fragile structures withstand an environment that is essentially a continuous, high-energy hurricane? The leading hypothesis points to an unseen inner strength. While they appear small on the sky, these globules must be orders of magnitude denser than a typical Bach globule. Their central cores could be so incredibly packed with material that their own immense self-gravity provides a powerful anchor, holding them together even as their outer layers are being violently stripped away. It's the difference between trying to blow apart a loose pile of leaves, which scatters instantly, and trying to blow apart a solid ball of clay, which might only erode slowly. However, density alone might not be the full answer. Another compelling possibility involves the invisible hand of magnetism. If these globules are threaded with powerful, ordered magnetic fields, those fields could be providing a crucial form of internal support. The magnetic pressure would act like a reinforcing scaffold within the cloud, creating a resilient structure that resists being torn apart by the external radiation. This would be akin to the difference between a sandcastle, which collapses in the wind, and a brick wall, which stands firm. The trouble is, directly measuring the magnetic field strength inside such small, distant objects is an immense technical challenge that we are only now beginning to tackle. Perhaps the most tantalizing question raised by their survival is whether it is linked to their potential for creation. Could the very process of their erosion be triggering star formation within them? As the intense radiation compresses the globules from the outside, it could be dramatically increasing the pressure in their shielded interiors. This external squeeze might be pushing dense cores over the critical threshold for gravitational collapse, forcing them to ignite into new stars even as the surrounding cloud is destroyed. We are actively searching for the infrared signatures of such newborn protostars deep within Thackeray's globules, but the evidence remains elusive. If protostars are indeed present, their own gravitational pull would add another layer of stability, binding the globule more tightly. If not, then we are forced to conclude that these dark tadpoles are simply far more massive and robust than their graceful appearance suggests. Cosmic survivalists holding their ground in one of the most hostile environments the galaxy has to offer. Venturing now into the constellation of Cepheus, we find another dark pillar engaged in a dramatic cosmic struggle, one whose form is so evocative it has earned the name the Elephant's Trunk Nebula. This colossal column of cold gas and dust, officially known as VDB 142, wins its way through the glowing expanse of the immense emission nebula IC 1396. Its shape is unmistakable, a long, sinuous trunk reaching out from a darker, more massive body of cloud, appearing to drink from a luminous pool of stellar energy. The entire structure is a sculpture in progress, And the artist is a brilliant, massive star known as HR 8286, the dominant member of the young star cluster at the heart of IC 1396. This O-type star is the primary source of the powerful ultraviolet radiation and fierce stellar winds that are relentlessly eroding the entire molecular cloud complex. The elephant's trunk is what remains a dense, resilient filament that has so far withstood the onslaught, its distinct shape carved out by the very forces that seek to destroy it. The surface of the trunk facing the star is brilliantly illuminated, a sharp, bright rim where the radiation is ionizing the gas and boiling molecules away into space. This creates a constant, inward-pushing pressure, compressing the entire pillar and giving it its defined, streamlined form. It is a breathtaking demonstration of stellar feedback, where the energy output from a star directly shapes its natal environment. But the central, gripping mystery of the elephant's trunk lies not in its spectacular erosion, but in what that erosion might be causing deep within its shielded interior. The tip of the trunk and several locations along its length are studded with small, intensely dark and compact knots. These are globules within a globule, even denser pockets of material that have managed to shield themselves from the radiation. And within these tiny, dark wombs, infrared and submillimeter telescopes have detected the faint warmth of nascent stellar objects. This discovery pushes the fundamental question of triggered star formation into sharp focus. Is the immense pressure from HR 8286's radiation actually catalyzing the birth of this new generation of stars? The mechanism is compelling. As the radiation-driven shockwave compresses the entire elephant's trunk, it increases the density and pressure inside these already dense globules to a point where their own internal gravity can no longer be supported. The external pressure effectively squeezes them past their breaking point, initiating a gravitational collapse that would not have happened, or would have taken vastly longer, in a more quiescent environment. In this scenario, the destructive power of the massive star is directly responsible for creating new stellar life, a beautiful and violent cycle of death and rebirth. However, an alternative interpretation presents a more nuanced and equally plausible reality. Perhaps these dense globules, and the protostars forming within them, were already on the verge of collapse before the full force of HR 8286's radiation ever reached them. The original molecular cloud from which the elephant's trunk formed was undoubtedly turbulent and lumpy, naturally containing these dense cores. In this view, the external radiation and wind are not the primary trigger, but rather a dramatic environmental factor that is simply shaping the context of the birth. It might be accelerating the process slightly, or determining the final masses of the stars by stripping away some of the surrounding gas before it can accrete, but it did not initiate the collapse itself. The stellar embryos we see would have formed anyway. The massive star's influence is merely a spectacular, and perhaps misleading, backdrop. Disentangling these two possibilities is one of the most active areas of research in star formation. It requires precise age dating of the young stars inside the trunk's globules, and comparing them to the age of the massive central star itself. If the protostars inside the trunk are significantly younger than HR 8286, it strongly suggests their formation was triggered by its radiation. If their ages are similar or older, then they likely began their collapse independently, and the feedback cycle we are witnessing is more about destruction and shaping than it is about true creation. The elephant's trunk, therefore, stands as a magnificent cosmic laboratory, a single structure that encapsulates the entire, complex debate over how stellar feedback truly operates, forcing us to ask whether the most massive stars are the architects of new solar systems or merely the demolition crews that clear away the ruins of their own birthplaces. While the elephant's trunk demonstrates the dramatic interplay between destruction and potential creation, our next destination reveals a truth that is far more subtle, and in some ways even more profound. Tucked away in the constellation of Cygnus lies a seemingly unremarkable patch of darkness catalogued as Lin's Dark Nebula 1014, or LDN 1014. For decades, this object was listed among countless other dark nebulae as a classic, starless Bach globule. It appeared in optical telescopes as a simple, isolated blot of blackness against the starry background, a textbook example of a quiescent cloud of cold gas and dust, perhaps in a long period of dormancy before any future collapse. It was, by all accounts, a cosmic waiting room, empty and silent. That all changed when we pointed the powerful eyes of infrared space telescopes in its direction. What those observations revealed was nothing short of revolutionary. LDN 1014 was not empty at all. Hidden deep within its opaque, dark heart was an incredibly faint point of warmth, the signature of an object so young and enshrouded that it barely qualified as a star. This was not a mature T-Tauri star like those in Lupus 3. This was something far more primordial, one of the youngest and least luminous protostars ever identified, an object in the very first moments of its existence. This discovery completely redefined LDN 1014. It was not a starless cloud. It was a stellar womb in the earliest possible stage of labor. The object at its center is what astronomers call a very low luminosity object, or a VLLO. Its luminosity is astonishingly feeble, only a few times greater than that of our planet Jupiter. This minuscule energy output tells a dramatic story of a birth that is happening at an incredibly slow and inefficient pace. The protostar is likely in its main accretion phase, slowly pulling material from a small, surrounding disk of gas and dust. But the process is not generating the fierce heat and light we associate with even young stars. It exists in a state of precarious balance, a faint ember struggling to ignite into a true flame. The existence of this hidden infant forces a fundamental and unsettling question upon astronomers. If a cloud as seemingly inert and classic as LDN 1014 was secretly harboring such a young protostar, then how many other so-called starless dark nebulae are actually doing the same? Our traditional method of classifying a dark nebula as starless relies heavily on the absence of detectable light in the optical and near-infrared wavelengths. But as LDN 1014 proved, the earliest stages of stellar formation are so deeply embedded, so heavily veiled by their natal dust, that they are completely invisible to those types of observations. They are hidden in plain sight. This suggests a staggering possibility that a significant fraction, perhaps even a majority, of the isolated dark globules we see scattered across the galaxy are not dormant at all. They are active stellar nurseries, their central cradles so effectively shielded that they give no external sign of the momentous events unfolding within. This realization challenges our most basic definitions in astrophysics. When exactly does a collapsing cloud of gas officially become a star? Is it at the moment the core first begins to heat up? When nuclear fusion tentatively flickers on? Or is it at some later point when it achieves a stable luminosity? LDN 1014 and its hidden VLLO blur these lines entirely. The object at its center possesses a dense core. It is actively accreting material, and it is influencing its immediate environment. Yet it emits so little light that it would be virtually undetectable without our most advanced technology. It exists in a gray area between a mere cloud and a true star, a cosmic newborn that defies easy categorization. This one, small, dark spot in the sky forces us to confront the humbling likelihood that our census of infant stars in the galaxy is profoundly incomplete, and that the quietest, darkest corners of space may be the most active nurseries of all. But the story of stellar birth is not always hidden in small, isolated globules. Sometimes the incubators are monumental, reaching for the heavens themselves. Soaring through the star fields of Scorpius, you'll find a structure of such imposing grandeur it seems to defy the very nature of cosmic architecture. This is the Dark Tower, a colossal dark nebula complex formed by the intertwined clouds LDN 1034 and LDN 1035. It is not merely a cloud, it is a skyscraper of shadow, a towering pillar of dust and gas that stands out against the Milky Way with the stark profile of a fortress or a chess piece. Its dimensions are staggering, stretching over nearly 40 light-years from base to tip, a scale so immense it dwarfs our entire local stellar neighborhood. What we perceive as a single, monolithic structure is, in reality, a complex and dynamic network. When observed with telescopes that can peer into its cold heart, the Dark Tower reveals itself not as a solid object, but as a tapestry woven from multiple, incredibly dense cores. These are the seeds of future solar systems, massive knots of material scattered throughout the towering pillar-like rooms in a vast, empty hotel. This intricate internal complexity is the first clue to its enduring mystery. The most immediate and profound question the Dark Tower presents is a simple one of structural engineering. How can something so tall, so narrow, and so massive possibly hold itself up? On Earth, a structure of such proportions, built from gas and dust, would collapse under its own weight in an instant. In space, without the benefit of steel girders or concrete foundations, the cloud relies on a delicate balance of invisible forces to maintain its spectacular shape. The most likely source of this support is a powerful internal magnetic field. Picture the entire Dark Tower as being threaded with lines of magnetic force, like the grain in a piece of wood. These fields can provide immense rigidity, creating a kind of cosmic skeleton that resists the crushing force of gravity, preventing the entire pillar from simply crumpling in on itself. However, magnetism is not the only possible architect of this stability. The interior of the cloud could be a maelstrom of turbulent motion. The random, churning movements of the gas within could generate a form of internal pressure, much like the chaotic bouncing of air molecules in a balloon keeps it inflated. This internal turbulence could be pushing outward with enough force to counteract the inward pull of gravity, at least for a time. The true puzzle is that we don't yet know which of these forces is dominant, or if they are working in a delicate partnership. The geometry of the Dark Tower itself adds another layer of complexity. Its narrow, elongated shape is far from the ideal, stable sphere of a cloud like Barnard 68. This extreme form makes it exceptionally vulnerable. Any small perturbation, the gravitational nudge from a passing star, the shockwave from a distant supernova, or even the gradual loss of internal pressure as the gas cools, could be enough to upset its delicate equilibrium. This leads to a fascinating paradox. The same internal support that grants the tower its current stability might also be stifling its primary purpose, to create stars. Those dense cores we see embedded within it are brimming with potential, but they are being held in check. The magnetic fields or turbulent motions that hold up the grand structure could also be providing just enough support within each individual core to prevent them from collapsing into protostars. The Dark Tower, therefore, exists in a state of prolonged suspense. It is a collection of stellar cradles, all fully furnished and supplied, waiting for the signal to begin the work of creation. That signal will likely come when the cloud's internal support system finally fails. If the magnetic field slowly decays, or if the turbulent motions gradually subside, gravity will finally win its long battle. The collapse would not be a single event, but a cascade. The densest cores would likely be the first to succumb, igniting into new stars. Their birth could then trigger a chain reaction, their radiation and winds compressing nearby regions and setting off further rounds of star formation throughout the pillar, ultimately leading to the tower's glorious but destructive dissolution. So, this magnificent dark spire stands as a monument to a temporary and fragile peace in the cosmic war between pressure and gravity. A breathtaking reminder that the most spectacular structures in the universe are often those poised on the very edge of catastrophic change. Moving from the immense, solitary structures we've explored, we find a celestial object that demonstrates how darkness and light can collaborate to create one of the most intricate portraits in the cosmos. In the constellation of Orion, not far from the familiar glow of the Orion Nebula, lies Messier 78, or M78. To the casual observer, it appears as a hazy, blue-white patch, a beautiful reflection nebula where the light from young, hot stars scatters off a surrounding blanket of fine dust, like a street lamp illuminating a foggy night. But if you look closer, with the penetrating gaze of a powerful telescope, the true masterpiece reveals itself. M78 is not just a smooth, glowing cloud. It is a cosmic tapestry, a luminous canvas that has been slashed and etched by a complex, web-like network of dark, obscuring filaments. These are not mere voids. They are distinct dark nebulae, with Barnard 206 being one of the most prominent, weaving through the glowing gas like rivers of black ink spilled across a brilliant blue page. The contrast is breathtakingly dramatic. The brilliance of the reflection nebula doesn't just highlight these dark lanes, it is actively being carved up by them, creating a stark, three-dimensional landscape of radiant peaks and profound, shadowy valleys. This intricate relationship between light and shadow forces us to confront a pattern that seems to be a fundamental rule of the cosmos, a pattern we see everywhere we look in the galaxy. Why does the interstellar medium, the gas and dust between the stars, appear to clump and fragment in this way, on every conceivable scale? From the sprawling complexes like the Cygnus Rift, down to the slender filaments of the dark Doodad, and now within a single nebula like M78, right down to the tiniest, thread-like dark lanes that are barely resolvable, we see the same basic architecture repeating. It's a cosmic Russian nesting doll, where every large cloud is made of smaller clouds, which are in turn composed of even smaller filaments and knots. This self-similar pattern, appearing again and again at different magnifications, is what scientists call a fractal structure. It suggests that the same physical processes that govern the collapse of a giant molecular cloud complex hundreds of light years across are also at work, in a scaled-down way, within a small dark lane inside M78. The central question then becomes, what universal process is responsible for this hierarchical fragmentation? The prevailing answer points to a combination of two competing forces, gravity and turbulence. Think of the original cloud of gas and dust not as a calm, static pool, but as a stormy, churning ocean. This turbulence, likely seeded by supernova explosions, stellar winds, and the sheer gravitational pull of the galaxy's spiral arms, creates a chaotic mess of shocks and compressions. Within this turmoil, gravity begins to act. It doesn't pull evenly on the entire cloud. Instead, it seizes upon the random density fluctuations created by the turbulence. A slightly denser region will have a slightly stronger gravitational pull, drawing in more material from its surroundings, making itself even denser and more massive. This process happens not once, but simultaneously on many different scales. The largest turbulent eddies create the biggest clumps, the great dark clouds. Within those large clumps, smaller eddies and motions create smaller filaments and knots, like Barnard 206 within M78. And within those smaller filaments, even tinier motions can create the dense cores that will one day collapse into individual stars and planetary systems. It's a cascade of structure, a bottom-up assembly driven by chaos and then refined by gravity. Understanding this fractal nature is not just an academic curiosity. It is absolutely key to creating accurate models of how stars form across the entire galaxy. If we can crack the code of how a cloud like the one surrounding M78 fragments, we can apply that same physics to predict the star formation activity in a giant complex 100 times its size. It provides a universal blueprint. The dark lanes in M78 are therefore more than just dramatic scenery. They are a magnifying glass held up to the fundamental processes of cosmic construction. They show us that the path to building a star is not a simple, direct collapse, but a complex, hierarchical journey where the galaxy first builds the large-scale scaffolding of dark nebulae, and then meticulously carves that scaffolding into the fine, focused structures where new suns are finally born. Now we venture to a cosmic crossroads, a place that is perhaps the richest and most chemically complex nursery in our entire celestial neighborhood. Just a stone's throw away in galactic terms, a mere 460 light-years from Earth, lies the Rho-Ophiuchi cloud complex. This is not a single object but a sprawling, chaotic, and breathtakingly beautiful tapestry of creation. Here, dark nebulae, glowing emission nebulae, and ethereal blue reflection nebulae all intermingle, creating a scene of such vibrant contrast it feels like a universe being born before our very eyes. The dark lanes, primarily composed of the clouds Barnard 42, 44, and 45, are the central characters in this drama. They are not passive shadows. They are dynamic, frigid reservoirs where temperatures can plunge to just 10 degrees above absolute zero. And within that deep interstellar freeze, something miraculous is happening. These dark clouds are immense chemical factories, and the products they are manufacturing are the very precursors to life itself. For decades, astronomers have used radio telescopes to peer into these lightless regions, and what they've found is staggering. The spectrum of light coming from these clouds is not a blank slate. It is a forest of emission lines, each one corresponding to a specific molecule. We've detected simple carbon-based molecules like formaldehyde and hydrogen cyanide, but we've also found far more complex organic species, including alcohols like methanol, the simple sugar glycolaldehyde, and even amino acetonitrile, a direct precursor to the amino acid glycine, one of the fundamental building blocks of proteins. This discovery transforms our understanding of these dark nebulae. They are no longer just star cradles, they are molecular cradles, places where the raw chemical ingredients for biology are being assembled in the cold and the dark, long before any star or planet has even formed. This immediately presents one of the most profound questions we can ask about our place in the cosmos. How is it possible for such intricate molecular architecture to arise in an environment that seems so hostile to complexity? The deep cold and the pervasive darkness, which we might assume would shut down chemistry, are actually the very conditions that enable it. The secret lies on the surfaces of the microscopic dust grains that fill the cloud. In the vast emptiness of space, two atoms have a very low chance of meeting and sticking together to form a molecule. But when they land on a frigid dust grain, a kind of cosmic sticky tape, they lose their energy and become trapped. They can then slide across the grain's surface, a process known as surface diffusion, until they meet another atom or molecule. In the cold, dense environment of a dark nebula, these tiny, frozen laboratories are incredibly efficient. Simple hydrogen atoms can combine to form molecular hydrogen. Carbon and oxygen atoms can link up with hydrogen to form methanol ices. More complex chains can be built, reaction by reaction, all while shielded from the destructive power of ultraviolet radiation that would break them apart in more exposed regions of space. These ices build up in layers on the dust grains, creating tiny, frozen repositories of prebiotic material. This process suggests that the basic chemical groundwork for life is not a rare or special event, but a common and perhaps inevitable outcome of the physics and chemistry of interstellar clouds. The universe, it seems, is hardwired to create organic molecules. Yet, a critical mystery remains. We can observe these molecules from a distance, but the exact, step-by-step chemical pathways that lead from simple ices to complex prebiotics like amino acid precursors are still being painstakingly recreated in laboratories on Earth. The conditions inside a dark nebula are extraordinarily difficult to simulate perfectly. How important are specific catalysts, like the silicate or carbonaceous surfaces of the dust grains themselves? Could cosmic rays, high-energy particles penetrating the cloud provide just enough energy to kick-start certain reactions without completely destroying the delicate molecules. And perhaps most importantly, how do these fragile molecules survive the next, violent stage of the cloud's life? When a dense core within the Rho-Ophiuchi complex finally collapses to form a new star and planetary system, the resulting heat and radiation will blast the surrounding cloud. The prevailing theory is that this sudden warming triggers a brief, explosive period of chemistry called hot core chemistry, where the complex ices on the dust grains vaporize, creating a rich gas phase soup that allows for even more complex molecules to form. But this also poses a danger. Too much heat and radiation for too long will ultimately break these large molecules apart. The survival of these prebiotic ingredients likely depends on them being safely incorporated into smaller, cooler bodies in the outer reaches of the new planetary system, into comets and asteroids. These frozen time capsules could then deliver these primordial building blocks to young, terrestrial planets like the early Earth, seeding them with the chemical potential for life. The dark lanes of the Rho-Ophiuchi cloud complex are therefore more than just a beautiful backdrop. They are a window into the very first, faint stirrings of chemical complexity that, given the right conditions, can eventually lead to a living, breathing world. They force us to consider that the story of life on Earth may have begun not in a warm little pond, but in the deepest, coldest, and darkest corners of interstellar space. But for all the vast, sprawling complexes we've explored, some of the most perplexing dark nebulae are the ones that are practically on our cosmic doorstep. Hiding in plain sight within the grand constellation of Orion, there exists a small, pitch-black patch known as Lynn's Dark Nebula 1622, or LDN 1622. At first glance, it seems unremarkable, just another blot against the starry background. What makes it extraordinary is its location and the profound confusion it creates about the very space around our own solar system. This dark nebula is seen projected directly against the faint, reddish glow of Barnard's Loop, that immense, arc-shaped emission nebula that curves around Orion's belt like a celestial ribbon. Barnard's Loop is a colossal structure, a remnant of ancient supernova or stellar winds, located roughly 1,600 light-years away. LDN 1622, by stark contrast, is now believed to be one of the closest dark nebulae to Earth, with distance estimates placing it a mere 500 light-years away. This creates a bizarre and wonderful celestial illusion. We are seeing a nearby, small cloud of cold dust silhouetted against a spectacular background canvas that is more than 3 times farther away. It's as if you held your hand up in front of your face and saw it perfectly outlined against a distant mountain range. This coincidental alignment provides a stunning visual, but it also triggered a long-standing debate in astronomy. For years, the true distance to LDN 1622 was a matter of significant uncertainty. Was it part of the much more distant Orion molecular cloud complex, a family of famous nebulae like Orion and Horsehead? Or was it a lonely, local cloud, a separate entity altogether? Pinpointing the distance to an isolated dark nebula is one of the most challenging tasks in observational astronomy. The primary method involves measuring the dimming and reddening of the light from stars that lie behind it. By carefully analyzing how much starlight is extinguished and how its color is shifted, and by knowing the intrinsic brightness of those background stars, astronomers can build a statistical model of how much dust lies between us and those stars, and thus estimate the cloud's distance. For LDN 1622, these meticulous studies have consistently pointed to a local origin, placing it firmly within our own galactic neighborhood. This resolution, however, only deepens the mystery surrounding this object and others like it. The confirmed proximity of LDN 1622 forces a fundamental question about the three-dimensional structure of the space surrounding our Sun. We often imagine the solar system traveling through a relatively empty region called the local bubble, a cavity of hot, thin gas carved out by ancient supernova. But the presence of a dense, cold cloud like LDN 1622, so close to us, suggests that this local void is not perfectly empty. Instead, it is punctuated by small, isolated islands of darkness, rogue dark nebulae, that are not part of any major molecular cloud complex. These are the celestial equivalent of forgotten, small islands in a vast ocean. How many more of these isolated, small dark clouds are drifting, unseen, in the spaces between the stars in our immediate vicinity? They are incredibly difficult to detect because they don't have a bright background like Barnard's loop to be projected against. We might only notice them when they happen to fall directly in front of a rich star field or a distant nebula. Their very existence challenges our senses of the local interstellar medium and raises critical questions about their role in the broader galactic ecosystem. While a giant complex like the Pipe Nebula is a major stellar factory, what is the purpose of these small, isolated clouds? They are likely too small and lack the mass to form massive stars or large clusters. Instead, they might be the birthplaces of solitary, low-mass stars, much like our own Sun may have formed in a relatively isolated globule. They could also act as important reservoirs of cold, complex molecules, contributing to the gradual chemical enrichment of the galaxy as they are eventually dispersed by stellar winds or supernova shocks. Furthermore, their presence so close to us highlights the dynamic and clumpy nature of our journey through the galaxy. As the Sun moves on its orbit, it will inevitably encounter more of these small, dark clouds. In the distant future, passing through a denser region of interstellar dust could have subtle effects on the heliosphere, the protective bubble of solar wind that surrounds our planetary system. LDN 1622, therefore, is far more than a simple dark spot. It is a crucial signpost, a close-by marker that reveals the textured and uneven nature of our local interstellar environment, reminding us that even the space between the stars is filled with hidden structure and untold stories. Now, let's travel to a celestial landmark, a place where one of the sky's most recognizable shapes is defined not by what glows, but by what does not. In the constellation Cygnus, the Swan, you'll find the magnificent North America Nebula, a vast cloud of glowing hydrogen gas that, as its name suggests, bears an uncanny resemblance to the continent. But that familiar shape, that iconic outline of a cosmic coastline, isn't carved by the light itself. It is defined by a profound, intervening shadow known as the Gulf of Mexico Nebula. Officially catalogued as Lynn's Dark Nebula 935, or LDN 935, this dark cloud is the artist that sculpts the continent. It is the void that gives the form its meaning, a colossal bay of blackness that creates the illusion of a Florida peninsula and a Mexican coastline against the brilliant pink backdrop of the Emission Nebula. This is a perfect example of a cosmic silhouette, where our perception of a luminous object is entirely shaped by the dark structure in the foreground. The Gulf of Mexico Nebula is not a small feature. It is a massive, complex cloud of cold molecular gas and dust, situated between us and the incandescent gas of the North America Nebula. Its presence completely blocks the light from the region behind it, creating that distinctive dark gulf. Without this dark nebula, the North America Nebula would likely appear as a large, amorphous glow, lacking the specific character that makes it so memorable. This beautiful coincidence of alignment immediately prompts a deeper investigation into the relationship between these two very different kinds of cosmic structures. We see a cold, dark nebula and a hot, glowing one seemingly sharing a border, but what is truly happening at that frontier? Is the Gulf of Mexico Nebula simply a passive curtain, a silent, dark screen that happens to hang in front of a brilliant light source? Or is there a dynamic, physical interaction occurring at the boundary between them? The reality is far more active and violent than a simple shadow play. The same massive, energetic stars that are causing the North America Nebula to glow, primarily the brilliant star Deneb and its stellar siblings, are also bombarding the edges of the Gulf of Mexico Nebula with an unrelenting torrent of ultraviolet radiation. This creates a stark interface, a cosmic shoreline where the cold, neutral material of the dark nebula meets the hot, ionized plasma of the emission nebula. This boundary is known as an ionization front. As the intense radiation strikes the surface of the dark cloud, it doesn't just stop. It heats and ionizes the outer layers of the cloud's gas, stripping electrons from atoms and causing that thin layer to light up. If you look very closely at high-resolution images, you can often see a faint, bright rim tracing the outline of the dark nebula, a glowing coastline where the dark cloud is being physically eroded. This process is called photoevaporation. The radiation is effectively boiling away the dark nebula, molecule by molecule, blowing the material off into the surrounding space. This leads to a fascinating and unresolved question about the life cycle of interstellar material. Is the dark cloud merely a victim, slowly being dismantled and dispersed by its luminous neighbors? Or could it, in its destruction, be contributing to the very system that is destroying it? The material being ablated from the Gulf of Mexico Nebula is not vanishing. It is being injected into the hot, ionized environment of the North America Nebula. This introduces fresh, colder, metal-rich gas into the mix. This influx can cool the hot plasma locally, causing it to clump and potentially seed new conditions for future star formation. The eroded dust grains might also provide surfaces for new chemical reactions in this more energetic environment. So, the interaction is not a one-way street. The dark nebula might be a source of raw material, its dissolution feeding the complex ecology of its surroundings. Furthermore, the shape of the Gulf of Mexico Nebula itself is a clue to its history and stability. Its well-defined, coherent structure suggests it is a relatively dense and massive cloud, capable of withstanding the external pressure for a significant time. Its form is likely being sculpted in real time by the radiation pressure, much like the Elephant's Trunk Nebula, but on a much grander geographic scale. The unanswered question is one of timescale and ultimate fate. How long can this dark continent maintain its shape against the constant stellar onslaught? Detailed observations are focused on measuring the velocity of the gas at this ionization front to determine the rate of evaporation. The answers will tell us not only the future of this particular cosmic gulf, but will also refine our understanding of how bright nebulae are replenished and how the violent feedback from massive stars continually reshapes the galactic landscape, using darkness as their primary chisel. Our next object is a study in cosmic minimalism, a dark nebula whose defining feature is its almost alarming perfection. Lying in the constellation Cepheus, Linne's dark nebula 1165, often nicknamed the Ink Spot Nebula, is a small, profoundly dark, and almost perfectly circular patch against the starry background. Its symmetry is so precise it appears manufactured, a stark black circle drawn on the canvas of the sky, rivaling even the iconic perfection of Barnard 68 we encountered earlier. This simple, geometric beauty, however, masks a complex debate about what this shape truly signifies. In the chaotic and turbulent interstellar medium, such a flawless form is an extreme rarity. It suggests a cloud that has achieved a state of near-perfect hydrostatic equilibrium. This means the inward pull of its own gravity is exquisitely balanced by the outward pressure of the gas molecules within it, a delicate standoff that has allowed it to settle into this serene, spherical state. This kind of balance is not easily achieved or maintained. It requires a long period of quiet isolation, free from the gravitational tugs of passing stars or the disruptive shockwaves from nearby supernova. Therefore, One compelling interpretation is that the ink spot is an exceptionally old and stable cloud. It has found its perfect form and could, in theory, maintain this peaceful existence for many millions of years to come. A timeless, dormant relic of the galaxy's raw building materials. Its simplicity, in this view, is a direct clue to its great age and undisturbed history. Yet, there is a completely opposite and equally compelling possibility. This perfect symmetry might not signal stability, but instead, signify a state of extreme precariousness. Imagine a ball balanced perfectly on the very peak of a steep hill. It appears motionless and stable, but the slightest nudge will send it tumbling downward. The ink spot could be in a similar metastable state. Its perfect balance might be the final moment of calm before a catastrophic gravitational collapse. The cloud could be poised on the very brink, its core density having slowly increased to a critical threshold where even the smallest perturbation, a slight increase in density from a chance collision with a smaller cloudlet, or a subtle change in the external radiation field, could be enough to shatter the equilibrium. In this scenario, the nebula's perfect shape is not a sign of great age, but a herald of an imminent and dramatic transformation. A deep breath held before the explosive exhalation of star birth. This duality makes the ink spot a fascinating object of study. Determining which of these futures awaits it is incredibly difficult. Astronomers probe its interior by observing how it dims and reddens the light of background stars, carefully mapping its density profile from its diffuse edges to its mysterious center. If the density increases smoothly and sharply toward a very dense, compact core, it would strongly suggest that collapse is already underway or is about to begin. If, however, the density is more uniform throughout the sphere, it would support the idea of a long-lived, stable cloud. Current observations hint at a dense center, leaning toward the imminent collapse theory, but the data is not yet conclusive. This uncertainty about its stability is intertwined with another puzzle, its origin. How did such a perfectly isolated, spherical cloud come to be, floating alone in its patch of space? There are two primary theories, each with profound implications. The first is that the ink spot formed in situ, meaning it condensed right where we see it from a larger, more diffuse field of interstellar gas. Over eons, random motions and the gentle pull of its own gravity could have slowly gathered the material, and as it contracted, it naturally settled into the most efficient shape for an isolated, self-gravitating cloud, a sphere. This would make it a prime example of the bottom-up build-up of structure in the galaxy. The alternative theory is far more dynamic. The ink spot might be a cosmic runaway, a fragment that was violently ejected from a much larger, tumultuous molecular cloud complex during a period of intense star formation. The gravitational interactions between dense cores within a busy stellar nursery can be chaotic, sometimes flinging a smaller globule out into the emptiness of interstellar space at high speed. As this ejected cloud traveled away from its turbulent birthplace, it could have settled down, its shape smoothing into a sphere as it escaped the disruptive influences of its former home. If this ejection scenario is true, it would mean the ink spot is not a pristine, primordial object, but a refugee, a piece of a larger structure that has found solitary peace far from the storm of its creation. Determining its velocity relative to the local standard of rest could provide a clue. A very high, peculiar velocity might be the telltale sign of a violent ejection in its past. So, this small, simple spot of darkness floating in Cepheus is anything but simple. It represents a fundamental question about the life cycle of interstellar material. Is it a dormant seed, content to exist for eons in perfect balance? Or is it a ticking clock, a stellar egg moments away from hatching? Its perfect shape offers no easy answer, serving instead as a quiet, profound reminder that in the cosmos, the greatest mysteries can often be found in the most simple and symmetrical of forms. Now, let's follow one of the most extensive and elegant dark rivers in the entire sky. a structure that seems to connect the very fabric of its stellar neighborhood. Winding its way through the constellation of Ophiuchus, Linne's Dark Nebula 1773, more poetically known as the Dark River, presents a breathtaking sight. It appears as a long, meandering band of cosmic silt, a shadowy current flowing through the star clouds, so prominent and continuous that it genuinely resembles a waterway carved into the heavens. Its scale is immense, stretching for nearly 20 degrees across the sky, which translates to a physical length of dozens of light years. This is not an isolated cloud. It is a galactic artery, a filament that appears to physically link several distinct hubs of stellar activity, including the Rho Ophiuchi cloud complex we explored earlier. Its form immediately suggests a function beyond mere shadow. The central, captivating idea is that the Dark River might not just be a passive, static structure, but an active pipeline, a conduit that is channeling the raw material for star formation from a vast reservoir into the specific, intense stellar nurseries we observe. The visual connection is so compelling it's difficult to ignore. The river seems to flow directly into these bustling regions of birth, as if delivering the gas and dust necessary to sustain their prolific output. This introduces a revolutionary way of thinking about galactic ecology. Instead of each star-forming region simply collapsing from its own isolated pool of gas, they could be fed by these long-range filamentary networks. The dark nebulae we see would then be the visible part of a galactic circulatory system, the veins through which the lifeblood of the galaxy. Cold molecular gas is transported to the sites where new stars are assembled. The dynamics of such a system are incredibly complex. For material to truly flow along this river, it must be moving in a coherent direction, streaming from an area of higher density or pressure toward an area of lower pressure, likely one of the active gravitational wells represented by the star-forming hubs. This isn't a simple, smooth flow like water in a pipe. The river itself has a complex internal structure, with its own turbulence, magnetic fields, and localized knots of density that could act as temporary dams or accelerators. The driving force behind any such large-scale flow is the primary mystery. One dominant theory points to the overarching gravity of the galaxy itself. As the Milky Way rotates, it creates density waves that spiral through the galactic disk. These waves can sweep up gas and dust, compressing them into these long filaments and potentially creating the pressure gradients that initiate a flow along their length. It's akin to the way wind blowing across an ocean's surface can drive the currents beneath. Another possibility involves the gravitational influence of the star-forming regions themselves. As a massive cluster like the one in Rho Ophiuchi forms, its collective gravity can reach out and pull on the surrounding interstellar medium, drawing material inward along the most convenient pathways, which would be these pre-existing dark filaments. The river, in this scenario, is being siphoned. A third, more subtle force could be at work: the gentle but persistent pressure of cosmic rays and stellar radiation from nearby stars, which can exert a force on the dust grains, slowly pushing them along the magnetic field lines that are likely threaded through the river, guiding the flow in a specific direction. So, is the dark river actually flowing? Observational evidence is beginning to provide tantalizing clues. By using radio telescopes to measure the subtle Doppler shifts in the light emitted by specific molecules within the river, astronomers can map the velocity of the gas along its entire length. Early results are not showing a simple, uniform current. Instead, the motion appears chaotic, with different segments of the river moving at different speeds and sometimes in slightly different directions. This doesn't disprove the pipeline hypothesis. It merely reveals its complexity. The flow may be intermittent, or it may be happening in a stop-start fashion, triggered by specific events like the shockwave from a distant supernova or the periodic gravitational tug from a passing spiral arm. Some sections might be collapsing locally to form their own stars, while others are faithfully transporting material to the larger hubs downstream. Understanding this dynamic is absolutely crucial for building accurate models of how our galaxy, and galaxies in general, form stars. If these large-scale flows are real and efficient, they would solve a fundamental problem in astrophysics: how star-forming regions can sustain their high rates of birth over millions of years without running out of fuel. A localized cloud of a certain mass can only produce a certain number of stars before it is dispersed. But if that cloud is continuously being replenished by a galactic pipeline like the Dark River, its star-forming lifetime can be dramatically extended. This turns the galaxy from a collection of isolated, short-lived fireworks into an interconnected, sustainable ecosystem, where material is constantly recycled and redistributed along these dark, flowing highways. The Dark River, therefore, is more than just a beautiful silhouette. It is a potential key to understanding the grand, cyclical choreography of cosmic material, a slow-motion current that may very well be carrying the future of entire stellar generations within its dark, meandering banks. But to truly understand the power a dark nebula can hold over the human imagination, we need to look no further than our 21st destination, which brings us back to that nearby cloud in Orion, LDN 1622. While its scientific story is one of local geography and cosmic alignment, its popular name reveals something much deeper about our own psyche. This is the Doodad Nebula. Look at a deep image of this object, and the reason for the nickname becomes chillingly clear. It doesn't appear as a simple, round globule or a gentle, meandering river. Instead, its form is jagged, chaotic, and sprawling. Against the faint, ethereal red glow of Barnard's loop, the Doodad Nebula looks like a monstrous, shadowy hand reaching out from the void, or a spectral, hooded figure looming in the depths of space. Its tendrils are irregular and sharp, creating a visage that is inherently unsettling, a Rorschach test in the stars where our brain instinctively patterns recognition onto the formless dark, and what it finds there is fear. This projection of dread onto a simple cloud of cold dust and gas is a fascinating phenomenon. It forces us to confront a profound question that lies at the intersection of astronomy and psychology. Why do we, as a species, so consistently imbue these cosmic voids with such ominous and threatening qualities? The answer is woven into the very fabric of our evolutionary history. For our ancient ancestors, darkness was not empty, it was full of potential danger. The night concealed predators, rival tribes, and the unknown. A deep-seated, instinctual fear of the dark, known as nyctophobia, is a primal survival mechanism hardwired into our brains. We are biologically programmed to be hyper-vigilant in darkness, to see threats in ambiguous shapes, to feel a chill when light vanishes. When we look up at a dark nebula, we are not looking with just our rational, modern minds. We are gazing through the eyes of our ancestors, and that ancient, subconscious part of our brain sends a clear signal that emptiness is not safe. It is a place of concealment, of mystery, of the monstrous. This instinct is then amplified and shaped by our culture. For millennia, human storytelling has used darkness as a metaphor for evil, the unknown, and death. Our myths and folklore are populated by creatures that thrive in the shadows: demons, ghosts, and of course, the boogeyman itself, that formless entity used to frighten children into obedience. Darkness is the canvas upon which we paint our deepest anxieties. When we apply the name boogeyman to LDN 1622, we are engaging in a timeless act of cosmic myth-making. We are personifying the void, giving a face to the abyss, because a named fear is often easier to confront than an anonymous one. This psychological projection has a direct impact on the scientific narrative, often in subtle ways. Consider the language we use. We describe these nebulae as swallowing light, as being profound voids, as sinister silhouettes. This is not the neutral language of physics. It is the charged language of narrative. It creates a frame through which we interpret what we see. casting the dark nebula in the role of a cosmic antagonist to the heroic, life-giving stars. But what if we flipped that narrative entirely? The darkness of the Doodad Nebula is not a destructive force. It is a creative one. That same opaque dust that blocks the light and creates such a fearsome silhouette is also a protective shield. It is what allows the deep, quiet chemistry of prebiotic molecules to occur, safe from the destructive radiation of nearby stars. It is the very material that, under the gentle crush of gravity, will one day coalesce into new solar systems, perhaps with planets that orbit within a warm, life-giving Goldilocks zone. The terrifying, grasping hand we perceive could, in reality, be a nurturing cradle, a closed fist holding the seeds of future worlds. This dichotomy is the ultimate lesson of the Doodad Nebula and all its dark kin. They are cosmic Rorschach tests. What we see in them says less about the nature of the universe and more about the nature of ourselves. Do we see a monster in the dark, or do we see a womb? The nebula itself is neutral. It is simply a cloud of dust following the laws of physics. The fear, the awe, the stories, these are all human contributions. They are the result of our ancient brains meeting the infinite cosmos and trying to make sense of the sublime. So the next time you see an image of the Doodad Nebula, with its terrifying, shadowy form, recognize that the fear you feel is 1,000,000 years old. But then, push past that primal instinct. See it for what it also is, a testament to the creative power of darkness, a reminder that what we fear most in the universe might just be the very thing that makes our existence and the potential for countless other lives possible. The true mystery is not in the nebula's darkness, but in our profound and complicated relationship with it. Floating within the rich star fields of the constellation Cygnus, there exists a dark nebula whose form is so distinct it seems to have been designed rather than born from chaos. This is the Propeller Nebula, officially catalogued as Linne's Dark Nebula 227. To the telescopic eye, it doesn't appear as a simple blotch or a winding river, but as a structure with two distinct, curved blades of darkness, sweeping away from a central hub in a configuration that uncannily mimics a twin-bladed aircraft propeller or perhaps the outstretched wings of a great celestial bird. This is not an illusion of projection. Its shape is a genuine, three-dimensional architectural marvel of dust and gas, and its existence presents a fascinating puzzle for astronomers. How does the random, turbulent interplay of gravity and pressure produce such a specific, almost mechanical, symmetry? The prevailing theories attempt to pinpoint the sculptor, and they lead us in two very different, yet equally compelling, directions. The first possibility is that we are witnessing the dramatic influence of a hidden, newborn star. Deep within the central hub of the propeller, there could be a powerful protostar, a stellar infant in the violent throes of its accretion phase. Such young stars often eject material in powerful, bipolar outflows, twin jets of gas screaming away from the star's poles at supersonic speeds. These jets can carve vast cavities in the surrounding molecular cloud, sweeping the ambient gas and dust into towering, wing-like structures. In this scenario, the propeller's blades are the fossilized remnants of this energetic excavation, the lingering impression of a stellar tantrum that cleared away the surrounding material and left behind this beautiful, sculpted void. The central hub would then be the dense envelope of dust still surrounding the protostar, hiding it from our direct view. However, an alternative explanation looks beyond a single central actor and toward the grand, invisible forces that permeate the galaxy. The propeller's remarkable form might be a direct imprint of the interstellar magnetic field. Imagine the cloud's dust grains as tiny, needle-like particles. In the presence of a powerful, organized magnetic field, these grains will align themselves perpendicular to the field lines, like iron filings around a magnet. This alignment can cause the cloud to collapse and contract more easily along the direction of the field, while resisting collapse across it. If the local magnetic field in this region has a specific, hourglass-like geometry. It could naturally channel and compress the cloud material into this distinctive two-lobed, propeller-shaped structure. The form we see would then be a cosmic fossil, a snapshot of the magnetic field's architecture frozen into the very dust it helped to arrange. Adding another layer of complexity, powerful turbulence within the original cloud could have interacted with this magnetic field, creating the specific curvatures and sweeps in the blades, much like wind shaping dunes in a desert. This magnetic and turbulent sculpting would not require a central protostar at all, making the propeller a magnificent example of large-scale interstellar physics at work. The challenge and the core of the mystery lies in distinguishing which of these forces is the primary artist. Observations seek the telltale signs of both. Astronomers use infrared and submillimeter telescopes to peer into the central hub, searching for the warmth and specific molecular emissions that would betray the presence of an embedded protostar and its powerful jets. So far, the evidence is ambiguous. There are hints of youthful stellar objects in the region, but none have been conclusively pinned to the propeller's heart as the definitive engine of its shape. Simultaneously, mapping the magnetic field through starlight polarization is an intricate task, but it offers the potential to see if the field lines indeed trace the elegant sweep of the dark blades. The propeller nebula, therefore, stands as a crucial test case. Its unusual morphology challenges the standard, more simplistic models of cloud formation, which often struggle to produce such clean, bilateral symmetry without a clear central driver. It forces us to consider that the evolution of dark nebulae is not a one-size-fits-all process. Some may be shaped by the explosive birth of stars from within, while others are molded by the patient, external hands of magnetism and turbulence. The true answer for the propeller might even lie in a combination of these processes. A protostar's outflow might have initiated the form, only to have its final shape refined and defined by the pervasive magnetic field. This one, uniquely shaped shadow in the sky reminds us that the universe is a master of many different sculpting techniques, and sometimes it chooses to sign its work with a signature as precise and enigmatic as a propeller spinning silently in the void. And now, our journey brings us face to face with a predator of the void, a creature of shadow with a form so striking it seems to have leapt from the deep ocean into the depths of space. In the constellation of Cepheus, you can find Linne's dark nebula 1235, more famously and fearsomely known as the Dark Shark Nebula. Its silhouette is unmistakable. A long, sleek body, a pointed head with a distinct snout, and even trailing, fin-like appendages that complete the illusion of a great white shark gliding silently through a sea of stars. The resemblance is so potent it feels intentional, a piece of cosmic art designed to capture our imagination. This immediate, visceral recognition is a perfect example of a psychological phenomenon called pareidolia, our brain's hardwired tendency to perceive familiar patterns, especially faces and figures, in random or ambiguous stimuli. We see a man in the moon, a face on Mars, and here, a shark in a cloud of dust. This instinct is a powerful engine for public engagement with astronomy. An image labeled Dark Shark Nebula is infinitely more captivating and shareable than one labeled LDN 1235. It gives the cosmos a personality, a hook that draws people in who might otherwise scroll past a more technical astronomical image. It transforms an abstract scientific object into a character in a cosmic story, making the vast and impersonal universe feel a little more familiar, a little more accessible. This is the undeniable power of pareidolia in science communication. It builds a vital bridge between human curiosity and complex celestial phenomena, inviting everyone to look up and see a story written in the stars. But this very strength forces a profound and nuanced question upon scientists and communicators alike. Once we have been captivated by the shark, once the initial wonder has drawn us in, where do we go from there? Does this compelling shape have any actual scientific meaning? Is the shark's form a mere accident of our perspective, a random alignment of dust that just happens to look like a predator from our particular vantage point? Or could its distinctive anatomy be a genuine clue, a direct physical manifestation of the forces that sculpted it? This is where the paths of public engagement and rigorous scientific analysis can diverge, and finding the balance between them is a delicate art. The most straightforward and likely explanation is that of a chance alignment. We are looking at a two-dimensional projection of a complex three-dimensional structure. The shark's body could be a long, tubular cloud, its fins smaller, unrelated filaments of dust that, from our precise location in the galaxy, appear to be attached. Its menacing profile might be the result of a simple, erosive process where the radiation from a nearby star has photoevaporated the cloud, carving out the snout and jawline in much the same way the Cone Nebula was carved. In this view, the shark is a beautiful and engaging illusion, a cosmic coincidence that tells us little beyond the cloud's basic composition and the presence of local stellar winds. Its shape is a delightful bonus, not a scientific datum. However, we cannot dismiss the possibility that the shape is physically significant. The shark's streamlined, hydrodynamic form is, in essence, a structure that is efficient at moving through a resisting medium. While space is not a liquid, the interstellar medium through which this cloud moves does exert a pressure. If the dark shark nebula is indeed plowing through a region of hotter, more diffuse gas, perhaps as part of a larger cloud complex moving through the galactic disk, its shape could be a direct result of that interaction. The head would be the leading edge, compressed and shaped by ram pressure, much like the bright-rimmed cloud LDN 1774, while the trailing, filamentary fins could be wisps of material being stripped away in its wake. In this scenario, the pareidolia is not pointing to a random shape, but to a specific physical process, hydrodynamic stripping. The shark-like form becomes a crude indicator of the cloud's motion and interaction with its environment. Its silhouette, therefore, could prompt a legitimate scientific investigation. An astronomer might ask, is there a measurable velocity gradient across the nebula? Does the head show signs of stronger compression or a different chemical signature compared to the tail? By studying the shark not as a shark, but as a morphological puzzle, we might uncover real data about the dynamics of this particular region of space. The ultimate challenge, and the core of the balance between communication and analysis, is to let the public's wonder be the starting point, not the conclusion. A skilled communicator will use the shark to capture attention, but then gently guide the audience beyond the familiar shape. They might say, "It looks like a shark, and that's an amazing coincidence." But what's even more amazing is what that shape might actually be telling us about the invisible forces of pressure and motion that are sculpting the galaxy. This approach honors the initial engagement while elevating the discussion to the real science. It uses pareidolia as a gateway, not a cage. It acknowledges the human desire to see the familiar, but then invites us to appreciate the even greater wonder of the underlying impersonal physics. The dark shark nebula, in all its fearsome glory, ultimately teaches us a dual lesson. It reminds us of the power of narrative and pattern recognition in bringing the cosmos down to a human scale. But it also challenges us to look deeper, to see past the shark and into the complex, beautiful, and often random processes that paint these magnificent shadows across the night sky. The greatest mystery it holds may not be about its shape, but about our own perpetual struggle to interpret the universe, forever caught between the stories we need to tell and the physical reality we strive to understand. In the vast catalogue of dark nebulae, where many are celebrated for their dramatic shapes or famous locations, our next subject proves that significance often lies not in celebrity, but in utility. This is Lin's Dark Nebula 134, a relatively anonymous patch of darkness in the constellation of Cepheus. To the casual observer, it is nothing more than a small, unassuming blot against the starry background, lacking the imposing profile of the Dark Tower or the evocative form of the Shark Nebula. Yet, within the scientific community, this humble cloud has earned an esteemed role as a kind of cosmic reference point, a standard candle for one of the most fundamental and tricky problems in observational astronomy: interstellar extinction. Interstellar extinction is the combined effect of dimming and reddening that occurs when starlight passes through clouds of cosmic dust on its long journey to our telescopes. The dust grains, tiny specks of carbon and silicate smaller than a wavelength of light, are not neutral filters. They are far more effective at scattering and absorbing blue light than red light. This is why distant stars appear not only fainter but also redder than they truly are. Much like the sun appears deep red at sunset when its light passes through a thick layer of Earth's atmosphere. For astronomers, this is a constant and pervasive complication. If we want to know a star's true distance, we need to know its true brightness. But if its light has been dimmed and reddened by an unknown amount of intervening dust, our calculations can be wildly off. We could mistake a brilliantly luminous but heavily obscured star for a much closer, fainter one, completely distorting our three-dimensional map of the galaxy. This is where a cloud like LDN 134 becomes invaluable. Its great scientific virtue is its simplicity and isolation. Unlike the complex, multi-layered structures of the Cygnus Rift, LDN 134 is a well-defined, relatively isolated cloud. Astronomers can observe a large sample of stars known to be located far behind it, and carefully measure how much dimmer and redder they appear compared to similar stars just outside the cloud's border. By doing this, they can calibrate a precise relationship between the amount of reddening and the total dimming for the specific dust grains that make up this nebula. It becomes a controlled laboratory, allowing us to create a highly accurate extinction curve for this one patch of the galaxy. This curve is a fingerprint of the dust itself, revealing the typical size, composition, and structure of the grains in this region. This meticulous calibration, however, leads directly to a profound and unsettling question that underpins all of galactic astronomy. Is the dust in LDN 134 representative of all dust everywhere? Are the properties of interstellar dust grains uniform throughout the galaxy? Or do they change from one dark nebula to another? If we take the extinction law we so carefully measured for LDN 134 and apply it blindly to a star seen through a different dark cloud, like the Coalsack or the Pipe Nebula, are we introducing a hidden error into our distance calculations? The answer to this question is critical, because these measurements are the foundation for determining the distances to stars, the structure of spiral arms, and even the scale of the Milky Way itself. The evidence so far suggests that the universe prefers variety over uniformity. While the general principle of dust reddening and dimming light holds true everywhere, the precise details of the extinction curve do seem to vary in different galactic environments. In some regions, particularly those near sites of recent star formation, the dust appears to be more effective at absorbing far ultraviolet light. This could be because the grains there are slightly larger, perhaps having accumulated thick mantles of water and other molecular ices in the cold depths of a dense cloud, like frost building up on a window pane. In other, more exposed regions of space, where dust is bathed in harsh ultraviolet radiation from hot stars, the grains might be smaller and bare, their icy mantles having been blasted away. Some studies even point to the possibility of radically different grain shapes, such as fluffy, porous aggregates that scatter light very differently than the compact, spherical grains often assumed in simple models. A dark nebula like LDN 134, therefore, acts as a benchmark. By comparing its detailed extinction curve to those measured in other clouds, we are essentially taking a census of galactic dust diversity. We are asking whether the dark nebulae in the Orion Arm, where our solar system resides, are made of the same stuff as those in the distant Perseus or Sagittarius arms. The implications are staggering. If the dust properties vary significantly, it means there is no single, universal key to unlock the problem of interstellar extinction. A measurement that suggests a star cluster is 5,000 light-years away could be off by hundreds of light-years if we use the wrong dust law. It forces us to create a more nuanced, three-dimensional map of the galaxy's dusty infrastructure, where not only the amount of dust, but also its very character, changes from place to place. So this unassuming dark spot in Cepheus, by serving as a faithful and well-understood standard, challenges us to confront the beautiful complexity of our galaxy, reminding us that even something as seemingly simple as a speck of cosmic dust holds a universe of variation within it. But to truly appreciate the scale and interconnectedness of these cosmic shadows, we need to look no further than the Coalsack itself, that grand void in the Southern Cross. Tucked just beside this famous landmark, almost hidden in its vast shadow, is a smaller, lesser-known dark nebula, designated Lynn's Dark Nebula 171. While it lacks the dramatic presence of its celebrated neighbor, LDN 171 is a perfect example of a crucial but often overlooked reality in the cosmos. Dark nebulae rarely live alone. Instead, they congregate. They form families, clusters, and vast complexes, a hidden society of shadows bound together by gravity and a shared origin story. The Coalsack is not a solitary island of dust. It's the most prominent member of a much larger gathering, a sprawling clan of dark clouds known as the Coalsack Dark Cloud Complex, and LDN 171 is one of its quieter siblings. Seeing these two nebulae together, one famous and one obscure, forces a fundamental question about the architecture of our galaxy. What is the true relationship between these different-sized clouds? Are these smaller, isolated dark nebulae like LDN 171 simply fragments, broken-off pieces of a once larger cloud that was shattered by some ancient cataclysm? Or can they condense on their own, forming as independent entities from the diffuse interstellar medium? The answer is key to understanding the entire life cycle of the raw material from which stars are forged. The prevailing theory, supported by a wealth of observational data, strongly favors the idea of hierarchical fragmentation. Imagine a single, enormous cloud of gas and dust, perhaps dozens of light-years across, slowly collapsing under its own immense gravity. As it contracts, it doesn't do so smoothly. Inevitable fluctuations in density, coupled with the chaotic churning of internal turbulence, cause the cloud to break apart. It fragments like a droplet of water splitting into smaller droplets. The largest fragments become the great dark cloud complexes, like the Coalsack complex itself. But the process doesn't stop there. Within these larger complexes, gravity and turbulence continue their work, causing further fragmentation. A complex shatters into individual dark nebulae like the Coalsack and its companion LDN 171. And within those individual nebulae, the process repeats itself yet again, fragmenting into the dense, star-forming Bach globules and cores. It's a cosmic cascade, a bottom-up assembly where large structures are systematically broken down into the smaller, focused units where stars can finally be born. In this view, LDN 171 is not an independent entity. It is a direct descendant, a child of the larger Coalsack complex. They share a common parent cloud and a common history. This relationship is more than just theoretical. We can look for evidence of it. If they are part of the same family, they should be located at roughly the same distance from Earth. They should also show similar velocities, moving together through space as a coherent group. Astronomers use radio telescopes to measure the precise motion and distance of these clouds by observing the faint radio waves emitted by molecules like carbon monoxide within them. For the Coalsack complex, These studies consistently show that its various members, including the main Coalsack and smaller clouds like LDN 171, do indeed form a physically associated group, drifting together through the galactic disk. This familial connection has profound implications. It means that the story of a small, star-forming core inside LDN 171 is intrinsically linked to the grander story of the entire complex. The conditions that led to its formation, the specific turbulence, the magnetic field strength, the initial chemical makeup, were set on a scale much larger than the cloud itself. The fate of the complex as a whole will also influence the future of LDN 171. A supernova explosion going off nearby could compress it, triggering a burst of star formation, or it could violently tear it apart, scattering its material back into the interstellar medium. The life cycle of the small cloud is woven into the life cycle of the entire family. However, the universe always enjoys presenting us with exceptions. While hierarchical fragmentation is the dominant process, it is likely not the only one. In the more tenuous regions between the great spiral arms, far from the crowded stellar nurseries, it is possible for small, isolated dark nebulae to form independently. Here, random motions in the diffuse interstellar gas might slowly, over eons, gather enough material through chance collisions and gentle gravitational attraction to form a small, stable Bach globule without it ever having been part of a larger complex. Differentiating between these two origins, a fragment versus an independent formation, is a challenging task. It requires a galactic census, a detailed three-dimensional map of dust clouds and their motions. If we find a small, isolated dark nebula that is moving on a very different trajectory from any large complex in its vicinity, it could be a candidate for independent formation. But if it's moving in lockstep with a group of other clouds, like LDN 171 with the Coalsack, then its lineage as a fragment is clear. Unraveling these relationships is not just an academic exercise. It is fundamental to creating an accurate model of our galaxy's ecology. By mapping these dark nebula families, we are essentially drawing a family tree for the interstellar medium. We learn how material is gathered, organized, and ultimately converted into stars and planets. A giant complex might give birth to a massive star cluster, while a small, isolated globule like Barnard 68 might produce only a single, solitary star like our Sun. The hierarchy of the clouds directly dictates the hierarchy of the stellar systems they create. So the next time you gaze at the majestic Coalsack, remember that it is not alone. It is the head of a family, surrounded by smaller, quieter companions like LDN 171. Each of these dark nebulae, from the vastest complex to the most humble globule, is a chapter in the same grand story. A story of how chaos slowly gives way to order, and how darkness patiently gathers itself to eventually blaze forth into light. And so our journey through the shadows comes to a close. We have traveled from the nearby, haunting void of the Coalsack to the distant, predatory silhouette of the Shark Nebula. We have witnessed pillars of dust like the cone and the elephant's trunk being sculpted by stellar winds, and we have peered into the perfect, spherical enigmas of clouds like Barnard 68, wondering if they are timeless relics or stellar eggs on the verge of hatching. We have seen dark rivers like the one in Musca and the grand architecture of the Cygnus Rift, structures that shape our very view of the galaxy. Across all 25 of these enigmatic dark nebulae, certain profound mysteries have emerged again and again, weaving a common tapestry of questions that challenge our understanding of the cosmos. The first, and perhaps most fundamental thread, is the puzzle of the trigger. What is the final, precise nudge that pushes a stable, cold cloud over the edge into the glorious chaos of stellar birth? Is it the shockwave from a dying star, the gravitational pull of a passing spiral arm, or the relentless pressure of radiation from a brilliant neighbor, as we saw in the bright-rimmed clouds? We observe the conditions ripe for collapse, But the exact moment of ignition remains one of the universe's most closely guarded secrets. Then there is the invisible hand of magnetism. From the orderly star factory of Lupus 3 to the improbable, straight lines of the dark Doodad and the towering stability of the Dark Tower, we find compelling evidence that magnetic fields are the hidden architects of the cosmos, sculpting and supporting these structures on a grand scale. Yet, directly measuring the strength and configuration of these fields within the opaque heart of a dark nebula remains an immense technical challenge, leaving us to interpret their influence from the beautiful shapes they leave behind. We have also marveled at the sheer tenacity of these clouds, their ability to survive in the most hostile environments imaginable. Thackeray's globules persist in a hurricane of ultraviolet radiation, while the Gulf of Mexico Nebula stands firm against the illuminating power of the North America Nebula. Their survival forces us to ask what gives them such resilience. Is it immense density, powerful internal magnetism, or perhaps the very act of forming new stars within that anchors them against the storm? And perhaps most intriguingly, we have delved into the complex chemistry thriving in the deep freeze. The Rho-Ophiuchi cloud complex and others like it have revealed themselves not as sterile voids, but as cosmic kitchens where ices on dust grains are quietly assembling the precursors to life itself. This discovery transforms these dark nebulae from simple star cradles into molecular cradles, suggesting that the building blocks of biology are a natural and widespread product of the interstellar medium. The overwhelming conclusion from our tour is a simple but paradigm-shifting realization. These dark patches are not empty. They are not mere absences in the sky. They are presences. They are dense, dynamic, and complex structures, each one a reservoir of potential and a vault of unanswered questions. They are the universe's way of gathering its raw materials, of conducting its most delicate chemistry, and of setting the stage for the next act of creation. The mysteries they hold, the triggers, the magnetic blueprints, the secrets of survival, and the pathways to chemical complexity, are the very frontiers of modern astrophysics. And the next great leaps in understanding will come from the next generation of observatories. The James Webb Space Telescope, with its unparalleled infrared vision, is already peering into the hearts of these globules, searching for the faint warmth of the youngest protostars. Giant radio telescope arrays like the ALMA Observatory are mapping the intricate flows of gas and the magnetic field directions within these clouds with stunning precision. These powerful tools are turning these cosmic shadows into living laboratories, allowing us to test our theories and, without a doubt, discover new phenomena that will surprise us. So the next time you find yourself under a clear, dark sky, far from the city lights, I encourage you to do more than just admire the brilliant river of the Milky Way. Look into the dark spaces, seek out those profound patches of blackness. Let your gaze rest on the Coalsack near the Southern Cross, or trace the dark river of the Great Rift splitting the summer Milky Way. When you do, remember that you are not looking at nothing. You are looking at the raw material of future suns and planets. You are looking at cosmic laboratories where the laws of physics and chemistry are being tested in the dark. You are looking at the deepest questions we can ask about our origins, written in shadows against the light. We have explored 25, but there are countless more. Tell me which of these enigmatic dark nebulae captured your imagination the most. Was it the iconic Horsehead, the perplexing propeller, or the deceptively simple ink spot? Share your thoughts in the comments below. I am genuinely curious to hear which cosmic shadow you find the most mysterious.